Next, we consider a mass of 10 grams subject to a net force of 500 newtons exerted through a displacement of 20 meters. Implicitly, the force and the displacement are in the same direction because they're both given a positive sign and no other information is given about direction. So what do we know? Well, let's just stop and think a minute now. In the diagram we saw a minute ago, we know that the, if we know the mass and the net force, what can we find? We can find the acceleration because net force is mass times acceleration, and that's easily rearranged to tell you that acceleration is net force over mass. What else? If we know the net force and the displacement, well, that's the definition of the work done on an interval. So we can find the work. Now, I always advocate that once you're given information, before you look at what you're trying to find, you ask yourself, well, what can I find given this information? That way you don't lock up trying to find what you're looking for. You see what you can find, and then you look at what you're looking for, and you find that it's very likely one of the things you already figured out you can find, or it's going to be more closely related to one of the things you can find than it is to the original information, or some combination of what you can find and the original information will often lead you to the solution. Okay, well, what are we trying to find? Well, the first question, now if you read the questions, first question says, what's the acceleration? Well, we just saw how we would get the acceleration. We divide the net force by the mass. We divide our 500 Newton net force by our 10 kilogram mass. A Newton, remember, force, unit of force, which is a unit of mass times a unit of acceleration. A kilogram multiplied by a meter per second squared. We divide that by kilograms, and we get meters per second squared. And of course, the arithmetic is easy. 10 into 500 is 50. We find that the acceleration of this object is 50 meters per second squared. Okay, now what else can we find? Well, let's go to the next question. We haven't used the fact that we can find the work, but I'll bet that's going to come up soon. Of course, I've made up the problems, and I know it's going to come up soon, but you would ordinarily just bet that it's going to come up pretty soon. Now, we're given that the initial velocity is 0. Okay, well, now what can you find if you know the initial velocity? Now, you know the acceleration, you know the work, you know the displacement, you know the net force, and you know the mass. Okay, what can you find if you know the velocity? Well, you know that kinetic energy is mass, 1/2 mass times velocity squared. So we could find the initial kinetic energy, which is 0. Okay. Well, what else could you find? Though, if you know the initial velocity, well, you know initial velocity, you know acceleration now, since we just found that. And if we hadn't just found it, you would see here, if you made a note of what we can find from the 3 quantities that were given, that we'll be able to easily find the acceleration if we happen to need it. So we know initial velocity, we know the acceleration, and the displacement. Well, that's 3 of the quantities in terms of which we model uniformly accelerated motion. We know that we can either, now using those 3 quantities, reason out all the other quantities, or we can use the 4th equation to find VF. Okay, well, we can use, you would know from the fact that you have 3 quantities that you can either reason it out, in most cases you can, or you can use the equations in some way. And if you have to use the equations, then the 4th equation is usually the one you're going to want to use. Okay, so the 4th equation, well, we know what the 4th equation is. We're looking for VF. Okay, so we just take the square root of this side, and we find, okay, VF squared equals this, then VF is plus or minus the square root of this. So we plug our information in. V naught is 0, so we have a 0 here. What's our acceleration? Well, we've already calculated it, 50 meters per second squared. And if that question had not been asked, again, in the process of thinking about what you can determine just from the initial information, you would see that you could calculate the acceleration. You'd be able to calculate this. Okay, but we have it, so we're going to use it. And then the delta S is 20 meters. So we do the arithmetic. Those numbers multiplied to 2,000. And a meter over second squared times a meter is a meter squared over second squared. So we get the square root of 2,000 times the square root of meters per second squared. And that gives us, well, square root of meter squared per second squared is meters per second. Square root of 2,000 is 44.7. So we have 44.7 meters per second for our final velocity. Now, next question asks, well, if the initial velocity was 5 meters per second, and keeping with my tradition of writing down exactly what I don't intend to write down, it looks like I wrote down a VF here, doesn't it? Well, that should be a V naught to be consistent with the problem. Excuse me. If V naught is 5 meters per second, then what's VF? Well, we have the same relationship. It's just that now we have a V naught to square. And we get a 5 meter per second quantity squared, and then plus the same to a delta S, because the delta S is the same as before. The acceleration is the same as before because the net force and the mass are the same as before. Okay, so we get final velocity is the square root of 5 meters per second quantity squared plus this same quantity that we had up here. And that's going to end up, this is going to be meters squared over second squared. We saw already that this is meters squared over second squared, so we can add them. And we're going to get 2,025 meters squared per second squared. The square root of 2,025 is exactly 45. The square root of meters squared per second squared is meters per second. Now, let's notice something. We increased our initial velocity by 5 meters per second. Did our final velocity increase by 5 meters per second? No, it only increased by about 3/10 of a meter per second. Okay, so that will surprise people a lot of times. You say, well, if I got 5 meters per second more initial velocity, why don't I have 5 meters per second more final velocity, given all the other conditions being the same? Well, the key is simply that it's not the velocity, the initial velocity, that determines the final velocity in any linear sense. It's the square of the initial velocity that contributes to the final velocity, and you also have this term here, so it doesn't work out. And on a little higher level, you've got extra kinetic energy here, okay, and it's kinetic energy that adds. Velocities don't add. Kinetic energies do add, and you don't have all that much kinetic energy at 5 meters per second. Now, at 15 meters per second, remember kinetic energy goes as the square of the velocity, so you have 3 times the velocity. You'll have 9 times, 3 squared is 9, times the initial kinetic energy. So, if the initial velocity is 0, is 15 meters per second, we find that our final velocity does go up significantly, goes up to about 47 meters per second. Now, I didn't do the whole calculation. It would have been just like this one, except I'd have had a 15 here, which would have given me 225 meters squared per second squared when I squared it, which would have added to the 2,000, giving us 2,250 meters squared per second squared. And the square root of 2,250 is, round off to the nearest one, 47 meters per second. Okay? Okay, well, there's a little more, but I see some smudges on the board, so let me clean those up before we go on. Okay, well, we anticipated it earlier that we might well be asked for the work done by the net force. So we multiply, we are asked, so we multiply the net force, 500 newtons, by the 20 meter displacement. And we do that over here. 500 newtons times 20 meters is 10,000 joules. So the work done by the net force with this information is 10,000 joules. Now, Remember that when our initial velocity was 0, our final velocity was 44.7 meters per second. Well, an initial velocity of 0 implies an initial kinetic energy of 0. An initial velocity of 44.7 meters per second implies a kinetic energy of, left my 0.7 off of there. I'm going to sneak it in, but it's real tiny, so you probably won't be able to read it. Anyhow, this is 44.7 meters per second quantity squared. Don't have a good way to sneak that in. Okay, so our final kinetic energy is 1/2 the mass. Mass is 10 kilograms as before. 1/2 the mass times the square of the final velocity. And the final velocity is 44.7 meters per second. Well, when we multiply all this out, square it, do all the multiplication, we end up with something very close to 9,990 joules. So the change in kinetic energy, if our initial velocity is 0, is 9,990 joules. Now, we'll note this 44.7 is rounded off. The actual number, I think, is 44.72, as a matter of fact. And I think if you square the accurate number, this is going to come out accurate to 10,000. Okay, it's very close to 10,000. It's only off by 0.1%. This and this are very much the same. So what have we done? We've verified that when the initial velocity is 0 for this situation, the change in the kinetic energy is effectively equal to the work done by the net force. It is equal, and the only difference between these two numbers is just due to a little bit of round off. We only have 3 significant figures here. We only get 3 significant figures of accuracy. Okay, now the initial velocity 15 meters per second. Do we get the same change in kinetic energy? Well, our initial kinetic energy, 1/2 mv0 squared, we calculated 15 meters per second for our v0, 10 kilograms for our mass. You can verify that we end up with 1,125 joules. Final kinetic energy, 1/2 mass times final velocity squared. Final velocity is now 47 meters per second, and that comes out about 11,000 joules. So what's our change in kinetic energy? Well, 11,000 joules minus 1,125 joules is 9,975 joules. Okay, well, again, there's round off. The 47 is rounded off. And the 11,000 joules isn't exactly what you get when you square 47 meters per second here and multiply it by the mass anyway. Once again, our change in kinetic energy, 9,975 joules, is very close to the 10,000 joules, only off by the round-off error. So what we've done is we've confirmed in this case that the change in kinetic energy is equal to the work done by the net force. So we see that this set of calculations down here is confirming that the work done by the net force is equal to the change in the kinetic energy. And I'm not sure this is written clearly enough to read completely, but I'm saying that this confirmation is no surprise, because where did we get delta W net equals delta kinetic energy, change in kinetic energy? Work done by the net force is change in kinetic energy. We got that by substituting A equals F net over M, which we get from Newton's second law, into the fourth equation of motion. And how did we get all this information here about the final velocity? We used the fourth equation of motion. And then we applied the definition of kinetic energy and work and made our confirmation, which is nothing but really coming full circle from our original definition.